Welcome back, students. This section 4.6 part 3 would be on radioactive decay. We will discuss about a model which gives a which represents mathematically the process of radioactive decay of a radioactive element. So there are substances like radioactive substances which decay, or that means which emit electrons, so which decay in size, that means they become less in size, so which decay upon emitting radiation. They emit radiation. They have the radiation that they emit, and during that process the quantity of it will decrease as the time passes by, so that will be like years together. So the rate of decay is proportional to the mass of the substance. So that means the more the mass, the more the decay. Okay, so this is analogous to population growth, except that the mass decreases. So physicists express the rate of decay in terms of half life, which is the time it takes for a given sample of a substance to decay it into half of its original mass. So if you are taking 100 grams, it should become 50 grams. So to become 50 grams upon decaying, so how much time does it require? That would be the half life of the object. Okay, so that half life is common irrespective of the mass that you take. So for example, radium 226 will have will has a half life of 1600 years. So that means if you take a initial sample, for that to reduce into half of its initial size or initial mass, it would take 1600 years. So that means for if you take 100-gram sample, for it to reduce to 50 gram, that is to decay it into 50 grams, so you need 1600 years. And for it to reduce to 25 grams, you need 1600 into 2 times, that is 3200 years, and so on. So in general, for a radioactive substance with mass, initial mass say m naught, that is represented, and half life say h, okay, the amount remaining at time t, okay, is modeled by m of t is equal to m naught times 2 to the power of negative t by h, where h and t are measured in the same time units. Like if h and t, h is measured in minutes, t will also be measured in minutes. If it is in hours, days, years, and so on. So to express in the form of exponential using e term, okay, e as a base, so we can write this as m of t is equal to m naught times e to the power of rt, correct? So to express the given model in this way, we need to find a relative decay rate. So r would be relative decay rate in this case. So it was growth rate if it is population, but here it is decay, therefore it is relative decay rate. Since h is the half life, we have m of t to be equal to m naught e to the power of negative rt. So this is the model. And what would be m of t for t to be h? So that would be half of the initial one, that is m naught m naught divided by 2, correct? So m naught times e to the power of r times h. So for h, that is at half life, so the quantity that remains is half of the initial mass, correct? So now this is nothing but, this is h is half life. Okay, this is nothing but half is equal to e to the power of negative rh. So now applying ln on both the sides, ln of half is equal to ln of e to the power of negative rh. So this would be R is equal to ln of 2 divided by h. So we solve for R. This is the solution for R. So this last equation allows us to find the relative decay rate R from using the half-life h. Okay. So so to define